We'd like to go now and show you what I think is one of the most beautiful views of the Earth taken, and it was taken 2 years ago with the Galileo spacecraft as it flew past the Earth the first time. This is the Galileo movie. It's a rotation movie, and I'm just going to let it run, and what I want you to do is look at it, look at the sun glinting off the oceans. The sun also glints off of rivers and lakes when it passes over South America and Australia. If you look carefully, you can also see clouds moving during this rotation film. So we'll be back right after that and discuss the Earth. Hi, we're back, and joining me is Carl Sagan, an interdisciplinary scientist on Galileo. And Carl, thanks for coming down. And I guess it's a good day for you, and a good day for Galileo. We're back at the Earth, and one thing I want to ask is, it's been 2 years since Galileo has come by. What do we expect to see this the second time?
That we didn't see the first.
We didn't see the first.
Well, let's see. There's night-side imaging, lightning, and maybe signs of a technical civilization on Earth. Mm-hmm. There's polar clouds and aurorae that are going to be, or are in the process of, being looked at. We will have high-resolution photos of an inhabited part of the Earth. Mm-hmm. I mean, last time the highest resolution was Central Australia and Antarctica, the least populated places on the planet. Now it's in the Andes, and there's lots of interesting features there, both in the context of the biosphere, but also the idea of patches of ice, isolated glaciers, the sort of thing, along with Antarctica, that you want to develop some experience for the Galilean satellites.
Mm-hmm. The movie we just saw is an interesting one. It's kind of a rare view that you see the Earth like that when the spacecraft is actually changing perspective and the Earth is rotating in the distance. To me, it's kind of analogous to the first Apollo images that kind of galvanized our view of the planet as a soul alone in space. And this is kind of the next generation view of that, much higher fidelity and much more realism.
It's I think it's emotionally tremendously powerful, and some of the things that will emerge along those lines later from the second Earth encounter, including the Earth as a little sphere rotating and the moon going around it, ought to be extremely powerful, I think.
Yeah, those data are going to be acquired in the next few days, and it'll take us a few weeks or a month or so to put those together into a movie, so we'll be looking forward to seeing those.
Well worth waiting for. And by the way, another picture in that same category is the Voyager 1 photo of the Earth as a point of light, as seen from beyond the orbit of Pluto. I think that also is an exquisite calibration of the fragility, vulnerability of our planet.
That's right. I know you've been thinking quite a bit about the biosphere and what we would learn from this interplanetary perspective. If, for instance, we didn't live here and we flew past the Earth with Galileo, what would we really learn about the Earth? Would we know it had a biosphere? We'd know a little bit about the atmosphere. But even things like the ocean, there's some question as how we would interpret the data.
Yeah, I'm going to be talking about this at some length tomorrow afternoon in Von Karman, but let's pick up on the ocean. What sequence of arguments could an extraterrestrial use to deduce this quite astonishing fact that the Earth is mainly surface liquid water? No other object in the solar system is anything like that. So first off, you would know just from the heliocentric distance how far the Earth is from the Sun, and from the luminosity of the Sun what the equilibrium temperature of the Earth ought to be in the absence of a greenhouse effect. Mm-hmm. And that would turn out to be 35 centigrade degrees below the freezing point of water. And it's clear from clouds that there's an atmosphere, so you would expect some greenhouse effect, and so you can see you're in the range of water. Water is cosmically extremely abundant. Then the NIMS experiment does radiometry. And so after this back-of-the-envelope calculation, you can actually measure from the thermal emission of the Earth at various latitudes the temperatures. And sure enough, the equatorial temperatures are comfortably above the freezing point. The polar temperatures are below the freezing point. There's this white solid stuff at the poles, probably the frozen form of water. There's this other stuff at intermediate latitudes, probably liquid form. Then also with NIMS, you can detect water vapor in the atmosphere. You can measure how much, and you can note that it is very close to the equilibrium vapor pressure of water vapor above a liquid. So now you have it. And then the specular reflection. Mm-hmm. If the Earth's surface were smooth, right, you could even get the index of refraction from the specular reflectivity. So I think it would be absolutely nailed down that we have surface oceans. And this is an example of how using a variety of sensors, you can find out a lot about a planet from flying by. One of the things that I was most interested to do is this. We've flown by some 60 worlds. We claim we haven't found life anywhere, and that is a significant result. That is, that we would have found life had it been there. Mm-hmm. But this has never been calibrated. We've never flown by the Earth with a modern interplanetary spacecraft, all instruments on, and detected life here. And so Galileo, because of this peculiar gravity assist Vega trajectory, mm-hmm, permits us to do that. And as I'll describe tomorrow, we find life in 5 or 6 different ways, including intelligent life. And this then means that the negative results that we find elsewhere are, in fact, significant.
Well, we've seen 60 different worlds, but many of them are just very low resolution, and clearly not with the suite of instruments available to us on Galileo.
Sure, that's certainly.
But it is good to be able to know at least that we've made some effect, our biosphere, our intelligent life, that we are at least visible with a kind of spacecraft like Galileo.
Yeah, it's in a way reassuring that we're visible, but most of what's visible is not us, it is us humans. It's microbes and plants.
That's right.
And cows.
Cows because of methane gas in the atmosphere. Right.
Flatulence is detectable over interplanetary distances.
Right. And termites also account for a lot of
Yes, it's true.
It's
true. And rice cultivation and,
right,
and natural gas leakage and so on.
When thinking last night a little bit about what's happened on the Earth in the last 2 years, basically it's interesting because the kind of things you're talking about detecting aren't the kind of things that we normally think about. I mean, we've had a major war. We've had 100 oil well fires, which blazed for several months and were put out.
Many hundred. I think it was much more than 100.
Yeah. We've had the world population increase by something like 200 million people. But it's interesting that it's all of those big things in our lives, all of our history, is really kind of pales compared to the kinds of things that Galileo is really sensitive to, the gross structures of the biosphere. Well,
and the planet itself. I mean, the Earth abides. You know, we we humans come and go and briefly set foot on the stage and then exit. And but that's just very small potatoes compared to what the Earth is involved with and knows about. It's an interesting question you raise. Could any of those events that loom so large in our lives have been detected by comparison of the 1990s?
For instance, like the oil well fires.
Yeah, the oil well fires, in principle, were certainly detectable, or would have been if we had flown by. I mean, we flew by in December, but they didn't begin until mid-January.
Right.
But if we'd flown by at the right time and looked down at night, I think they would have been detectable.
Okay, very clearly, yeah. What else? In terms of the products that we're getting now, we're going to getting this moon picture and this moon Earth mosaic and the Earth zoom. We're also going to be looking quite a bit at, I guess, Australia as the focus in a zoom out from very high resolution all the way out to I guess down to a pinpoint of light eventually with Galileo. As you point out, that's an unfortunate area in terms of humankind. It's basically almost uninhabited in terms of the high resolution areas we're going to be looking at.
Well, our high resolution, you know, is a kilometer per pixel or something of that order. So it's not high resolution by human standards. But I mean, the original vision that I had of the Zoom movie was something like this. You start with a single human being, photographed by helicopter.
Right.
And then you back off to helicopter altitudes, then you back off to aircraft altitudes, then you pick up with Galileo and keep zooming back, absolutely continuous until you're left with, as you say, the Earth as a point of light. The reality is extremely far from that continuous zoom, but nevertheless, we'll have a data product that just has never been done before. Some fraction of such a zoom with a number of interruptions.
One interesting aspect of life on Earth here is the fact that there is very little carbon dioxide in our atmosphere compared to the carbon dioxide in Venus's atmosphere closer into the Sun and Mars further away from the Sun. Now that carbon dioxide exists, or the carbon exists here, but it's tied up in the rocks.
That's carbonates.
And most of those rocks are buried. Is there any way that one could really understand that from a remote sensing spacecraft? I mean, it's an incredible structure geologically, these kilometer-thick deposits of carbonates which are buried under the oceans, buried in some of the rocks on land, but they're exposed in very few areas.
That would be tough. I mean, you could certainly discover, and in essence Galileo has, that the atmosphere is 3.5 times 10 to the minus 4 mixing ratio carbon dioxide, compared to
a small amount.
Yeah, I mean, you know, whatever it is, 0.03%. While carbon dioxide is the principal constituent of Mars and of Venus. And Venus, with a 90 bar atmosphere made mostly of CO2, it absolutely dwarfs the carbon dioxide content of the Earth. And so a reasonable question, if you came from somewhere beyond the terrestrial planets, is why this discrepancy? Or put another way, where did all the carbon dioxide in the Earth's atmosphere go? And could you detect it? There are carbonate absorption bands in the infrared, and I don't know, if you fly over the white cliffs of Dover or something, you might find there's occasional patches which seem to be rich in carbonates. Could you deduce directly from observation the fact that tens of bars of carbon dioxide are locked up as carbonates in the Earth's sedimentary column? I don't think that would be easy, but you could perhaps do it theoretically. That is, understand the carbonate-silicate equilibrium. It used to be called the Urey equilibrium, and the presence of water and substantial weathering, and maybe deduce that. But that's very different from having direct observations of it.
Right. Right. We've also, in the intervening 2 years, had some rather major volcanic eruptions, which have affected, or made a visible effect. When you look at the sunset, you can see the dust in the atmosphere. There may be some climatic effects as well. Are any of these things possibly detected with Galileo, or can we even deduce the fact that the planet is volcanically active?
Yeah, that's a good question. The solid-state image, the imaging experiment has a cluster of pictures over Hawaii at night. And
right now we've got a very good, healthy eruption going on.
That's
in Hawaii.
right, and designed, in fact, no coincidence, to answer the very question you've posed. And it'll be interesting to see if it's detectable and just how clear-cut, how unambiguous it is that these lights, if they show up, are in fact due to volcanism.
Are we only looking for light, or are we able to look for heat or any other signs, gaseous signatures?
I've forgotten whether NIMS is Bohr-sighted at the same time. I think probably yes. So if there were significant sulfur dioxide or something, maybe it could be detectable. But I'm only guessing. I've forgotten whether that's the case or not. But in principle, it should be possible. And I think it would be very hard to imagine a planet of the mass and radius of the Earth, as outgassed as the Earth is, without imagining there's substantial volcanism. And you would see island arcs. You would maybe some volcanoes, if you had resolution just a little bit better than a kilometer, volcanoes themselves might be detectable. I don't think it would be hard to see that this is a volcanically active planet.
One deep contrast that the Earth has that many of the other bodies that we've seen in the solar system has, there are very few craters on the surface. We have a very, very active weathering process. But there are some volcanic, some crater features. I guess there are even some in Australia. Are we going to be, is there any plans to look at some of these and understand those?
I don't think there's anything specifically targeted, but Meteor Crater, Arizona is of the order of a kilometer across.
Yeah, they're very small structures.
That is at or below the resolution limit. There are some residual, much larger craters, but you often have to struggle to find them even from aerial photography. So I think if it were a major goal, of a flyby, or especially an orbiter, you could probably find it, but it's not absolutely trivial to do. But apart from that, the argument would go, look, here's the moon right by the Earth in the same impact environment. Asteroids and comets that hit the moon are going to hit the Earth as well. How come the Earth is not nearly as cratered as the moon is? Never mind whether you find a few craters or not. And then, as you say, you would have to imagine that there's substantial weathering, and you'd have to try to understand what the weathering processes were. As soon as you had understood that the oceans were liquid water, it would be a very good bet that liquid water over long periods of time has a substantial effect in eroding and filling in craters.
Now, I'm amazed at how effective water is at erosion. We talked about the Andes Mountains in Chile, and I observed there quite a bit. And we go down there, and it's very near the Atacama Desert, which is the driest place on Earth. And even so, it only rains there perhaps once a century in some areas. And I'm startled that when you look at the terrain is predominantly, very, very clearly suffering from water erosion. I mean, even if it just rains once every century, still that's the dominant effect on the topography.
More than aeolian erosion.
Much more than any kind of wind erosions. I mean, you see some erosion structures on rocks from wind, but very, very clearly the valleys, the incised structures on the cliffs are all due to water.
So this is the great catastrophist uniformitarian debate in geology. To explain the landforms of the Earth, can you do it by the occasional drop of water, the motion of a mite over immense periods of time? Or, if you thought the Earth was only a few thousand years old, don't you have to imagine a sequence of catastrophes?
Right.
So what you're saying is one of the absolutely key debates in the history of geology.
Well, speaking of catastrophes, we've kind of gone away from catastrophism, but now we seem to be making the full circle and coming right back to it, in that some of the major delineations in geology appear to be associated with catastrophic events, mass extinctions, perhaps the impact of asteroidal material or comets on the Earth, perhaps even associated with massive areas of volcanism. Galileo has flown past an asteroid, and this is clearly something of major excitement to us, both in trying to understand what an asteroid looks like and also trying to relate that to the meteorites which fall on our surface. What did you think of the Gasper encounter, and
lovely.
look forward to the Ida encounter?
I thought the latest data processing by Joe Vaverka of Cornell and his colleagues is really spectacular. I mean, these odd-shaped, lumpy, battered objects in the main asteroid belt, and also the Earth-crossing family of asteroids. For the first time, we're getting to know them, and look forward to seeing Ida on our way to Jupiter. You know, in retrospect, the idea that Phobos and Deimos, the two moons of Mars that we were able to photograph close up here at JPL for the first time in 1971 with Mariner 9, that they are captured asteroids. At least the general appearance of Gaspra and the general appearance of Phobos, you could imagine them very well as neighbors or members of the same family.
Now that's a problem, though, isn't it? In capturing an asteroid like that without, you've got to release a lot of, similar to Galileo's going to Jupiter, and we've got to fire our engines to get into orbit.
Absolutely.
To capture an
The
asteroid.
mechanism of capture is tough, but the body looks like an asteroid. And I don't claim that should carry enormous weight, but we're getting to know this new category of object, of which there are immense numbers in the solar system, and so NASA now has another category of objects that have been observed close up for the first time in this preliminary reconnaissance of the solar system that's been going on at this institution for the last 30 years.
Yeah, I'm amazed that there are whole classes of asteroids, and they're based on color and physical properties, and there are a whole class of meteorites that fall to the ground, the iron ones, the stony ones, and mixtures of the two. And I guess lately, over the past few years, by cataloging and characterizing these kinds of sets, they seem to be falling into patterns, and maybe what we have on the ground are samples of some of these asteroids.
I think it's very likely, and not just the asteroids, but the Moon and Mars as well. Much rarer, for obvious reasons, hard to have an impact on those bodies, which splays out debris, which encounters the Earth, which falls on the Earth, and which is actually found. But even that is possible. On the other hand, there are some meteorites that don't seem to have any obvious asteroid that they come from, and some asteroids that seem not to be sampled in the meteorite population. And that might very well be one of various kinds of selection effects, including it's very hard to get samples from this family of asteroids to the Earth. So there's certainly a lot of work to be done there.
What's the current thinking on the origin of the asteroids now? Is there some failed planet on the way out to Jupiter that didn't make it? It's not a large amount of mass compared to an Earth mass.
No, it's quite right. Even allowing for huge numbers of small guys who we haven't seen. Classically, going back to the 19th century, there's two views. One is a remnant of the worldlets which formed the planets, which were prevented from forming by the presence of nearby Jupiter, and the other, much more difficult to justify, but
catastrophism.
Much more interesting, is that it was a world that was somehow blown up. Present opinion is much more strongly the former than the latter.
Even though some of the meteoric material appears to be coming from a very, very large parent body. I mean, we get pieces that look like cores, pieces that look like mantles, and pieces that look like crusts.
So there's no question there are collisions going on in the asteroid belt, and pieces are torn off and intercept the Earth, but that doesn't mean that the asteroids themselves come from a larger lunar-sized object that somehow got destroyed. But I think it's fair to say that nobody's 100% sure how the asteroid belt formed and why there's only one asteroid belt.
Let's look forward a little bit to the Jupiter encounter. Jupiter is by far one of the most spectacular places I have ever imagined, much less actually physically seen. It's reality. We've got worlds like Io, which I think even tax the imaginations of science fiction authors. Here's a place that geology changes in the time frame of weather on our planet. What do you look forward to in the encounter?
The first thing I look forward to is the probe, because this is something which is truly qualitatively new, unique. for the first time, in situ measurements in the atmosphere of a Jovian planet as the probe continues to go down, including chemistry. You know, the colors of Jupiter, which are wildly exaggerated in color-enhanced pictures, but nevertheless are really there, are due to something, some molecule called a chromophore. We call it that because we don't know what it is. What molecules are doing it? We don't know. And the organic chemistry, which organics are one of several possibilities, sulfur compounds, phosphorus compounds are the other two categories. But organic chemistry is certainly happening on Jupiter, and here we will have, including at depth down towards the water clouds, some direct information, and not just chemistry, but lots of other data. That's tremendously exciting, and that is a part of the mission that is not at all degraded by the possibility that we will only have the low-gain antenna to deal with.
All of that data will be stored on the spacecraft, and all of it sent back to the Earth.
That's right. So there's no terrible downsizing of mission design for the entry probe, as there is for NIMS and imaging, and that is very sad. Although the argument is, well, we'll just get the best data, but there's a lot of best data that is in the original mission design. But even there, the data for Jupiter, for the magnetosphere and trapped radiation belts of Jupiter, and for the moons, and I guess for the ring, all of that is just fantastic. And that's going to be a wonder a day, I think.
Yeah, Jupiter is such a complete system. With rings, with spectacularly different moons, and with an atmosphere which is almost psychedelic in its nature, the way the various colors and motions.
Yeah.
It's going to be quite an amazing area to see, and to pick and choose which data you want to send back is going to be real.
And what's clear is you have to give up on movies of cloud motions, and there's a lot of sad things if the
well, there's still a great deal of hope. There are things
right.
That,
if the antenna gets unfurled, that's going to be a cause for celebration.
Yes. Even still, I think the encounter is going to be rather spectacular.
No question about it. Even if we're stuck with the LGA, we're in business.
And Jupiter itself is kind of mimics the solar system in general. It's a system that probably formed together. The moons show a gradation of densities as they go out, maybe compositions, certainly geologic activity. And this too is a mystery that Voyager hinted at, and hopefully Galileo will more or less address that problem at higher resolution.
Yeah, absolutely. Have you ever, on this program, talked about your own observations of Beta Pictoris?
Well, no.
Well, it's time for somebody to interview you on that. I mean, that's an extremely interesting set of observations.
Well, that particular observation is kind of a hint that some of the nearby stars may also have formed planetary systems around there, and that's something maybe we'll discuss at a future time.
Okay, I just don't want you to hide your light in the bushel.
Okay. Yeah, I'm not. I'm not an anchor person. I'm an astronomer. So any mistakes I make can be blamed on that, and the early morning that we had to all wake up.
I don't think you made any mistakes.
Anyway, thank you very much, Carl. We really appreciate that. And finally, we'd like to just close and tell you that Galileo is now about 2 hours, 33 minutes from its closest approach with the Earth. It's at an altitude of 84,912 kilometers, 52,762 miles. It's traveling at a speed of 9.356 kilometers per second. That's a speed of 20,928 miles per hour. And finally, in closing, I'd like to give you my own personal observations of the Galileo-Earth encounter. Over the last 3 hours, we've been discussing some of the scientific results and expectations from these encounters. But however important these things may be, they really are just an hors d'oeuvre compared to the banquet of discoveries awaiting us at Jupiter in 3 years. To me, the most important contribution that Galileo will make as it looks back at the Earth for the last time is to allow us to see ourselves as we really are. Everything we normally experience, everyone who ever lived, all of our history takes place on or very near the Earth's surface. And we often refer to a global view as meaning the big picture or a worldwide view. But now Galileo reminds us that there is a larger perspective, a universal view, where our world is just one of many. In the next few weeks, you'll see the Galileo images of the Earth and Moon spinning alone against the enormity of space, the sun glinting off our oceans, and entire continents appearing like small islands. Remember that the Earth is just one tiny gear in the clockwork of the solar system, and Galileo is our emissary, now firmly off to give us that universal view, and we will share that view with anyone who will listen. This is Rich Terrell, an astronomer at the Jet Propulsion Laboratory, thanking you for watching on behalf of NASA and the Galileo project. Stay tuned. In 15 minutes, we'll have the Galileo press conference. Thank you. Bye-bye.